Okay, so in this thought experiment relating to the mass transport by photons, what we've established is that when the photon gets emitted from the left side of the box recoils and obtains a momentum kick to the left, and the momentum kick is equal to minus E over c, where E is the energy of the photon. Okay, and um, and that the box actually moves to the left during the time that it takes for the photon to travel from the left side of the box to the right side of the box. The box moves a distance that's equal to minus E over mc delta t, and the photon, of course, is moving too, and it moves a distance um, equal to the length of the box minus E over mc delta t. Basically, the length of the box minus how much the box moved. Okay. Um, So the key thing to understand here is that the force of the photon on the box and vice versa. So in order for the box to accelerate, um, that is, in order to go from stationary before the photon is emitted to, to a particular velocity v, it has to accelerate, and we know from Newton's laws that that requires a force. And so the photon basically pushes on the box and vice versa, and it pushes on the box. It basically gives an impulse to the box that's equal to the change in its momentum. Okay, but the key thing is that when it's absorbed, it gives an impulse to the box and vice versa. The key thing to understand is that these impulses, these forces, are internal to the box. Okay, because the photon's moving on the inside, and so there's no external force on this box. There's only internal forces that are being exchanged here. And what that means, if you remember from your first year mechanics class, is that the center of mass of the box can't move. Because if the center of mass of the box were to move, that would require an external force. Okay, so the center of the mass of the box must not move, but the actual physical, the box actually moved. We've established that. So the center of mass didn't move, but the box actually moved. And what that means is that the photon must have moved from some mass from the left to the right. So if the box physically, we see the box move to the left a little bit, but the center of mass of the box doesn't move, that means that some mass must have been taken from the left and moved to the right. Okay, some small bit of mass. So how much? Okay, well, in order for the center of mass not to move, then we have to have that some little mass mu, okay, this is the mass that's being transported by the photon, times times how far the photon moved, okay, has to be equal to the mass of the box times how far the box moved. Okay, and so first of all, delta xp and delta xb are obviously in different directions, so there's a relative minus sign between these two things. Again, mu is the mass that we're associating with the photon is transporting, and m is the mass of the box. Okay, so what that means is that this mass is equal to the mass of the box times how far the box moved relative to how far the photon moved. And we can basically just take the ratio here, delta xb over delta xp, and we get v delta t over c delta t. And if you basically work this out, okay, what you find is that you get E over c squared this is an E over c squared. This is mu. So this is the mass, the effective mass, the actual mass, which is transported from the left side of the box to the right hand side via the photon. This does not mean that the photon has mass, but it just means that the emission of the photon corresponds to loss of mass from that side, and the absorption of the photon corresponds to gaining of mass on that side. And so we see that photons can transport energy.